Okay, we're really happy to have Anna Wright here, visiting from CCA. Um, so Anna did her PhD at Rutgers, was then a postdoc at Johns Hopkins, and then moved to CCA. And I heard yesterday that she recently accepted a faculty offer. So congratulations. Um, yes, super exciting. And she will tell us all about stellar halos of dwarf galaxies. So go for it.
Hey, yeah. So thank you so much for having me here. This is actually my first time getting to give talks on the West Coast, I realize, in person. I gave a talk at UC Riverside during the pandemic, but that didn't really count because it was over Zoom. So it's been really fantastic to get to see San Diego and the beautiful campuses you guys have here at UCSD as well as at SDSU. Today I'm going to tell you a little bit about one of the projects I'm working on, looking at how the smallest galaxies in our universe form and evolve. But before I get into the details, I wanted to tell you kind of a little bit about my research in general. And the kind of one sentence summary of everything that I do is I use cosmological simulations to study objects, specifically galaxies and features of galaxies that telescopes have a difficult time seeing. So when most of us think of a galaxy, we're typically thinking of something fairly bright and massive, like our own Milky Way, or similar to this galaxy that I'm showing on the screen here. But if we probe deeper, we can see that there's far more to at least this galaxy than we might initially think. So we do, of course, have this kind of bright central stellar disk that is usually, kind of the first thing that pops into someone's brain. But in addition to that, we also have these little satellite galaxies that are orbiting this galaxy. And as we can see in this deep image, and which your projector actually shows really well, you can see that there is material coming off of one of these satellite galaxies. That's evidence that this galaxy is actually interacting with the larger galaxy at the center. And all of the satellite galaxies that I pointed out here are dwarf galaxies. So these are typically defined to be galaxies that have a mass that's about 10 times less massive than something like a Milky Way or smaller than that. And then in addition to having these little dwarf galaxies orbiting it and interacting with it, our central Milky Way-like galaxy here also has this big spheroidal component full of stars. And we have found structures like this around our own galaxy. We've also found them around a number of other galaxies. And thus far, observations indicate that somewhere between about 0.1 and 10% of a galaxy's stars actually live in this large spheroidal component that we call the stellar halo. And for a sense of scale, our own Milky Way has a disk that has a radius of about 25 kiloparsecs, but the stellar halo goes out to about 10 times farther than that. So really about halfway to our nearest massive neighbor, the Andromeda Galaxy. Now, in addition to being, very diffuse and very faint, this stellar halo also actually has quite a bit of structure, which is nice. So you can just barely see this. We have these kind of shells on the edge of this galaxy. And additionally, I pointed out a couple of stellar streams. So this kind of loopy thing over here, as well as this guy. And it turns out that structures like this actually give us a lot of information about how this galaxy is assembled. And to kind of explain why that is, I'm going to show you a movie of the formation of a stellar halo around one of the Milky Way mass galaxies in one of the simulations that I work with. So what you're going to see are on the bottom right here, this is all the stars. So this is every star that ends up bound to our central Milky Way analog at the end of the simulation. In each of the other boxes, though, you're only going to see stars that come from a single dwarf that ultimately interacts with this galaxy. So you can see the first one coming in now. The reason it's blue is just so you can keep track of where its stars are. The other two are going to be yellow and green. And watching this, you can hopefully see that the large stellar halo that our central galaxy develops here is primarily made up of stars from other galaxies that have fallen into its gravitational potential and then been ripped apart by tidal forces. And as these orbiting galaxies are disrupted, they form these incredibly complex streams of stars. And what's really amazing is that dynamical times are very, very long in the stellar halo because densities are so low. And so we can see imprints of these accretion events for billions of years after they happen. And that means that if we can detect stellar halos, we can use them to study the properties of galaxies that were destroyed billions of years ago, in addition to studying the history of the central galaxies that remain. In fact, studying the stellar halo of our own Milky Way is one of the primary methods that we've used to kind of learn about its assembly history. So, populations in the southern hemisphere have known about our galaxy's two largest satellites, the Small Magellanic Cloud and Large Magellanic Cloud, for a very long time. But we've discovered upwards of 50 more dwarf satellites of the Milky Way, particularly in the last like 15-ish years. And you can see 10 of them here in the StarCat image from Gaia. But these are really only the companions of our galaxy that exist as mostly gravitationally bound structures at the present day. It seems like there's a lot more going on. So if we look at the stellar halo of our galaxy, which you can, I just gestured at, you can kind of see it as like a faint fuzz here. What we see are remnants of the larger building blocks that contributed to our galaxy over its lifetime. What we think of as our galaxy is really not a single entity, it is an ensemble. When we look at the stellar halo, we see evidence of accretion. And by that, I mean we see clusters of stars as well as individual stars whose chemistry and kinematics are distinctive enough that we can associate them with individual merger events. And when we study the stellar halo of our own Milky Way, we see evidence of at least four-ish fairly major events in its history, although we think we might see evidence of quite a few more. So the four I've listed here are Kraken/Heracles, Sequoia, the Helmingstrom progenitor, and Gaia Sausage Enceladus. But in addition to these accretion events, we see probably remnants of upwards of 100 little dwarf things, as well as tons and tons of globular clusters. And so the Milky Way is very much an ensemble.
These are superimposed on the main galaxy. This is the event itself. It's not the this is not the Gaia sausage.
This is
superimposed on the main galaxy.
So these are dwarf galaxies from my various simulations. These are, things around the mass that these would have been, but probably not at the right redshift.
But you're showing is when they merge with the Milky Way, Milky Way analog, or just the progenitor?
Just the progenitor. So these scales here are definitely not remotely correct. This was more just an illustrative of like these things were all pretty substantial that came in. So the next question here is kind of what about the building blocks of the building blocks? Do these also have mergers that contributed to their formation? And if so, how far down does this go? How far down do we have to go before we find something that only forms stars inside of its own gravitational potential well, that didn't just, that didn't have a bunch of mergers that also contributed to it? Is there even anything like that, like a fundamental building block? Or is it turtles all the way down and every single galaxy has its own complex merger history that we might be able to explore? So if our galaxy and other massive galaxies like it are anything to go by, the place to look for the answer to this question is probably going to be the stellar halos of these little galaxies, because this is the only place where dynamical times are likely going to be long enough that we can see direct evidence of accretion at the present day. The problem is that this is already really hard for massive galaxies. Stellar halos are both very faint and very diffuse, and therefore very, very difficult to detect. And this problem we expect to just get worse as we move further and further down the mass scale, as you can probably guess, looking at how tiny these little galaxies get and how few stars they have. And because of that, it's perhaps unsurprising to find out that we still have very few observations or simulations of stellar halos around dwarf galaxies. We have been observing what we think are potentially stellar halos around local dwarfs since roughly the 1990s. But because these stellar halos are so faint, so diffuse, typically these observations consist of a few red giant branch stars in the outskirts of really, really nearby dwarfs. However, observations have made incredible progress, especially over the last 5 or so years, using targeted surveys of dwarf galaxies. And we're actually getting to the point where we're starting to map the stellar halos of a few local dwarf galaxies. And one of the ones that we actually already have really good data on is M33. So I don't, this is a small enough group. I don't know what your kind of background knowledge of M33 is. But in case you're not familiar with it, this is a fairly nearby galaxy. It is at the upper end of what we might consider to be a dwarf galaxy, and it lives on the outskirts of our massive neighbor Andromeda. And so it's a really good candidate for stellar halo studies. And so one of a couple of the collaborators that I have on this project, Laura Cullinane and Carrie Gilbert, participated in the Triangulum Extended Survey, or the T-REX survey, to basically get spectroscopic data of stars in M33's disk. And what they found was that, well, most of the stars were, in fact, disk stars. They appear to be rotationally supported. There was definitely a kinematically hot component that appeared to be something similar to a stellar halo. And so what I'm showing up here is M33 and with kind of the footprint of the survey overlaid. And if you squint, you can maybe see why they named it T-Rex. Little stubby arms.
They need some more hands.
Yeah, it needs some teeth too. I think they are hoping to add a little bit more to it. But, so I mentioned like M33 is an interesting case study. It's convenient because it's fairly nearby. But the other big thing is that because it's kind of at the upper mass range for what we would consider to be a dwarf galaxy, we might naively expect that its stellar halo would have properties that are kind of intermediate to what we see in more massive galaxies and what we might expect to see in less massive galaxies. But what the T-REX survey found was that is maybe not the case at all. And in fact, M33's stellar halo looks really weird. So the first kind of weird property that the T-REX survey found is that M33's stellar halo is weirdly centrally concentrated. So in more massive galaxies, what we tend to see is that the fraction of stars that are dispersion supported and members of the halo increases as you move outward from the center of the galaxy. In M33, it is the opposite. Almost the entire mass of the stellar halo is confined to the inner roughly 3 kiloparsecs. Another weird property is that the stellar halo appears to contain both old stars and fairly intermediate age stars. And in more massive galaxies, like the Milky Way, stellar halos are typically very much composed of extremely old stars. And finally, there's a bit of this halo that seems to actually be counter-rotating with respect to the disk, which is deeply weird. Thus far, we've tended to find that the stellar halos of massive galaxies are either not rotating at all, or that they have a very slight co-rotation with the disk. So what is going on here? Well, with a sample size of 1, it's really hard to tell. We can theorize, but that's kind of it. And so I think this is where simulations really come in. It is very difficult to observe the stellar halos of dwarf galaxies. It is a little bit easier to simulate them. And so with that in mind, I've been working with a new suite of dwarf galaxies to kind of examine the properties and formation of stellar halos in dwarf galaxies. The suite is the Marvelous Massive Dwarfs. This was run by a couple of my other collaborators on this project, Akasha Cruz and Allison Brooks. I won't go too deep into the physics in these simulations, although feel free to ask if you're interested. The important things to note are that these are zoom-in cosmological simulations of dwarf galaxies. So they start their evolution at a very early point in time, and they do evolve within like a self-consistent environment. There are 41 dwarf galaxies in the suite now, and they range in stellar mass from about 10 to the 8 to 10 to the 9 solar masses. So roughly from M33 mass down to about an order of magnitude less massive. And the kind of really exciting thing for me is that the star particles in these simulations are only about 1,000 solar masses. So star particle mass for most simulations, or most cosmological simulations, is really one of the limiting factors in studying diffuse regions like dwarf stellar halos. And that's essentially because if you have 10 to the 5 solar mass star particles, which is pretty typical for a cosmological simulation, and your dwarf stellar halo has 10 to the 6 solar masses worth of material in it, you have 10 star particles in your stellar halo. So you might be able to say that it exists. You can't really say anything else about it. And so having these smaller star particles means that we can start to kind of interpret the observations and hopefully make some predictions for future observations. Now looking at these, oh yeah, sure.
Sorry, just going back.
Yeah.
Could any of those weird features of M33 stellar halo be explained by interactions with them?
Maybe. The thing is, The most recent calculations of M33's orbit suggest it's on first infall, and it's still about, I think it's 230 kiloparsecs away from Andromeda. So it's unlikely that this is coming from an interaction with Andromeda. However, I do have a bit at the end, basically looking at another suite of simulations where we're hoping to start to incorporate the influence of bigger environments to see, if maybe the stellar halo is so incredibly delicate that you could start stripping it really early on. And that might explain why we see so few stars at larger radii. But yeah, it's definitely the fact that, so yeah, and these I should say too, like these are relatively isolated dwarf galaxies. They do have their self-consistent environment, but these are all specifically selected to be like SMC to M33 mass things that are pretty far away from anything supermassive.
And Andromeda might have taken certain.
Sorry, say that again?
If you have certain orbits around M33, maybe Andromeda would take that satellite before it merged with M33.
Oh, yeah.
M33 was closer at some point. Stellar stream. So I think it might not be related to what you're going to say, but I think the merger history of M33 might be very.
Yeah.
Because of M31.
It might be, yeah. And especially given that it formed on the outskirts of M31, so it's not forming in the same kind of environment as these galaxies, which is another reason why I'm really interested in the new suite that we will hopefully be starting to run soon, where we're focused on, dwarfs in more Milky Way-like environments. But looking at this, set of images, hopefully you can tell these dwarfs are quite diverse. So you can see that we have things that have, like a spirally structure. We have things that are very compact. We have some things that are just very asymmetrical and irregular. And when we look at the stellar halos of these galaxies, it turns out that they are also very diverse. So what I'm showing here are G-band surface brightness maps of the galaxies, and specifically only those galaxies in our sample that have disky morphologies. And you can see that despite the fact that I have selected these galaxies to have fairly similar-ish morphologies, it's about 2/3 of the sample that has disky morphologies, and to be in a fairly similar mass range, there's a lot of variation here. We have things that really just don't have much we would call a stellar halo, or like a few stars out. And then we have things that definitely have a stellar halo, or that one up there. We also have things that have a very smooth stellar halo that doesn't appear to have a whole lot of features, as well as others that definitely have distinctive things like streams and shells that to me scream out, hey, I'm a signature of accretion.
Are the stars of the halo or the dwarf galaxy results, or are they just like a continued?
So what I'm showing here is integrated light. So I have mapped the star particles onto 1.5 kpc by 1.5 kpc pixels, essentially. Let's see, this would be, I don't remember like the theoretical distance I said, but yeah, in this case, I'm thinking about integrated light. Yeah. But the hope is that with this level of diversity that we see here, we'll see at least a few that share properties with M33, and so we can, start to explain maybe the observations a little bit, or at least provide one explanation of, potentially many. So I'm going to start with the first kind of weird feature that we see with M33, which is that it has this very centrally concentrated stellar halo. So what I'm showing here on the x-axis, we have the galactocentric radius normalized by the scale radius of the galaxy. And if you're not used to thinking in scale radii, you can just think of this as normalized radius. And then on the y-axis, what I'm showing is the fraction of stars that are occupying halo orbits rather than disk orbits. In the red is the actual data from the T-Rex survey. So the stars show the average for each radial bin, and then the circles show what was measured in different halves of the disk. So you can get an idea of the level of variation that's seen throughout M33. And you can see that it does indeed have this very centrally concentrated stellar halo. And if I overplot the marvelous massive dwarfs here, you can see that we once again, perhaps unexpectedly, have a really large amount of variation. We have some that have kind of more flat stellar halos, and then we have others that have more of a rising profile, like what we might expect to see in a more massive galaxy. But we have a few that look quite a bit like M33. So we're going to take one of those and just look at how it came to have a stellar halo that looks like this. So I'm going to show you a clip from this galaxy's life. What I'm showing here initially, this is just gas density. in these kind of blues, greens, yellows, and pinks. And then you're going to see little blue spheres pop up that indicate the birth of new stars. So just to orient you, we have the main progenitor of one of our galaxies here at the center. And then coming in from the left here, we have something that isn't too dissimilar in mass. And these two galaxies are going to merge. And this is a very gentle merger. But the orientation that our secondary galaxy came in at ends up setting the orientation of the resultant galaxy's disk for the rest of its life. This galaxy has a pretty quiet merger history after this. And what this means in terms of the stellar halo is that first, pretty much all of the stuff that we see in the stellar halo is the result of just this one merger. Dynamical friction also means that because this thing is massive, it sinks pretty much straight to the center. And because this galaxy has a pretty quiet merger history after this, there isn't really a reason for its material that is, kind of initially kicked out from this merger, or any of the material for that matter, to get perturbed into very highly radial orbits later on. And so this is why we end up with this very centrally concentrated stellar halo. Now, this is an extreme example. I think this is the gentlest merger I've ever seen in a galaxy simulation. But we see some version of the situation where we have a very dominant major merger that sets the orientation of the disk in all of our galaxies that have very centrally concentrated stellar halos. Okay, so that's kind of a potential explanation for weird thing number one.
Can I ask
Oh,
just
yeah.
to make sure I understand? So these
Sure.
these measurements are in radial shells on the left plot.
Yes.
And so what is the typical, I don't know, pericenter to apocenter ratio of the stars? Like this at a moment in time.
Oh, yeah, this is at a moment in time.
How much do they move?
Oh, so these are, let's see. I don't think that I've looked at that specifically, because I've been thinking about this in terms of like M33, which we really just have one snapshot. I mean, I can tell you that they occupy halo orbits, but that's not helpful.
Right.
So I couldn't tell you how like radial their orbits are.
Yeah.
That's something to look into, though.
Yeah.
Yeah. And we can talk about this later. We have some sloshing. That's really weird.
And this establishes right after the merger. Check the profile. See.
So you mean like the central concentration?
Yes.
So this is measured, all of these are measured at redshift 0.
Yeah, but I was just wondering,
Yeah.
because merger was so gentle, I just don't know.
Yeah, so you should see this pretty quickly after the merger. You would have to wait a little bit to, you have to wait for the disk to settle down a little bit to have something that you would call a disk versus a halo. Actually, the galaxy that I have after this is one where the merger is later, and there is, I can actually show you which one that is. That is this one. And the merger is a little bit later. It's also a lot more disruptive, which I'll show you, but you have a little bit less central concentration. And some of that's, just because it is more disruptive. But you initially get this shell, and I would expect that to potentially settle a little bit as the disk settles, but I expect that to stick around. I think the reason, I think this would be very centrally concentrated very quickly after the merger. Because if anything, it should get fluffier with time. Yeah. Is that?
Yeah, we get the more for this.
Okay. Yeah. So kind of weird thing number 2 is that M33 has a lot of intermediate age stars in its stellar halo. So to do a comparison here, what I've kind of created a very simple way of looking at this, which is just looking at the difference between the age of the halo and the age of the disk. So on the x-axis, we once again have our kind of normalized radius, and then on the y-axis, we have this difference in age. So very old halos would be at the top of this plot, and very young ones would be at the bottom. And if we put the marvelous massive dwarfs here, you can see there's no real pattern here. We have a ton of variation in the ages of their stellar halos. But what we're going to do is we're going to take a fairly extreme one. So we're going to take this galaxy, and we're going to look at the video of kind of what happens to it to make it this way. And I've already told you a little bit. So this is a galaxy that you can see as you're looking at an edge-on disk here. So this is something that already has a settled disk. So this is going to be a slightly harder. So the angular momentum vector is basically pointing straight up at the top of the screen here. And the reason why this one has such a distinctive halo is that we have a major merger that comes in on a completely different orientation to the disk of this galaxy. And it ports our main progenitor here basically into adopting the orientation of the orbit it came in on. And that means that this merger is much more disruptive than the merger we just looked at. So the fact that it's later and the fact that it's more disruptive means that we have stars that are going to be on average younger at the time that we observe them getting perturbed into the stellar halo. That's, just from the get-go with the merger being later, but also because it takes much, much longer for this thing to settle down because this merger is so disruptive, we have these stars getting perturbed for longer. And so we end up with this much younger stellar halo on average. Okay, let's check out weird thing number 3. So this is that we have some counter-rotating stars in the stellar halo of M33. This is weird. Do we even have anything like this in the simulations? So once again, on the x-axis, we have our normalized radius. Y-axis here is going to be the fraction of stars in the stellar halo that are counter-rotating. And if I put the marvelous massive dwarfs on here, you can see that we actually have a little bit of counter-rotation at the center of pretty much every galaxy, and that's just because we have a really wide distribution of orbits at the centers of galaxies. However, there are a couple that definitely have more pronounced counter-rotation, and we're going to take this one, which has off-center counter-rotation, and have a look at why it's like this. So this, I think, is probably the simplest one. It was the one where I looked at the video and I was like, oh, yep, I know exactly what's happening here. So here's our main progenitor. This galaxy is rotating counterclockwise from our perspective. And then we have a little thing that comes in on clockwise orbit. Let's see if there, yeah. You can see that it does have stars in it. And it turns out that all of the counter-rotating stars that we see in the stellar halo are basically just from this one galaxy. Now, it's important that this is happening pretty late in the simulation. And so that means that these stars haven't really had time to do anything but orbit in the way that they were deposited. And so this suggests that potentially M33 had a fairly late minor merger on a counter-rotating orbit, maybe, assuming the simulations are correct and there aren't 1,000 more explanations for this.
A general question about it. Say that it has to be great because if time goes on, the counter-rotating part is disrupted by the potential of the galaxy. We have a rough idea that.
For like time scale?
Yeah, like when you get here, or
I don't know. I mean, Katherine Johnston probably does. But I can't, or Johnson. Sorry, my brain. I can't tell you off the top of my head. I could check and see how long it takes in the simulations, but there is almost definitely like an analytical answer to that.
If M33 has a recent version that creates this counter-rotating components, we expect to see any other relic of the like if we look at maybe like neutral hydrogen.
Potentially. So M33 does have a warp, like a little S-shaped warp in its neutral hydrogen disk. We don't know the source of that, and the fact that it is so far from M31 right now, and it seems to be on first infall, suggests it's not coming from M31. And so my pet theory based on this is that it's had a fairly recent, very minor merger, but there could also be a lot of other explanations for that. But it looks so normal when you look at it, and then apparently, like, it seems just like the deeper you get into looking at M33, it becomes apparent. It's deeply weird, just like every other galaxy, which is great. Yeah, so it seems like actually that we have succeeded in reproducing at least the kind of weird features of M33 with the marvelous massive dwarfs, at least kind of qualitatively. And what's more is that it actually seems like all of these features have a common origin. We have a centrally concentrated stellar halo as a result of a merger. We have intermediate H stars, the stellar halo. That is also caused by merger. We have a counter-rotating component in the stellar halo caused by merger. So clearly, the stellar halos themselves must be made of material from these mergers, right? That came in with the merging galaxies. They have to be just like the stellar halos of more massive galaxies, where it's basically all accreted material, right? Well, if I plot the fraction of stars in the stellar halo that formed in the body of the central galaxy itself, so this, the in situ fraction, it should be low for these galaxies, and it is not. Even if we just look at the 3 galaxies that have the most in common with M33, there's a variation in the in situ fraction, but it's still very high, out to about 6 scale radii. So these are not accretion-dominated stellar halos. They are in situ-dominated stellar halos. So what is going on here? How is it that we can work out information about the merger history of this galaxy from this in situ-dominated stellar halo, but the stars themselves don't come from the mergers? Well, this is essentially a result of something that I alluded to earlier, which is that as we move down the mass scale, your galaxies that are actually merging with your galaxy get more and more dark matter dominated. Our kind of leading theory of most of the matter in the universe is that it's cold dark matter, although obviously we have people here looking into alternatives. But one of the features of cold dark matter is that it's self-similar, and this has some interesting implications for potential merger histories. So if we take, for instance, the merger history of the Milky Way, and here we're just going to focus on the 4 contributors that I mentioned at the beginning of the talk. Kraken is thought to have inhabited a dark matter halo that's about 1/3 the mass of the Milky Way. So that's a 3-to-1 merger. Gaia Sausage Enceladus is thought to be a 10-to-1. The Helmingstrom's progenitor is thought to be about 15-to-1, and Sequoia is thought to be about 100-to-1. And because dark matter is self-similar, it is possible that something like M33 would have had a merger history that looked like this too, where the things that it merged with were roughly these mass ratios for it. The thing that would have been very different would be, of course, the baryonic mass. So the mass that came from stars and gas rather than dark matter. So I'm showing here on the x-axis dark matter mass, and on the y-axis the ratio of stellar mass to dark matter mass. This is from Baruzzi 2013. And so what we can see is that galaxies that are either very massive, really galaxy clusters, or very low mass have most of their mass coming from dark matter. There is an area right in the middle here where stars are thought to make up more than 1% of the mass of the galaxy, and this is right where the Milky Way lives. And so even something like, Gaia Sausage Enceladus, well, pretty dark matter dominated, would still have brought in quite a few stars. But once we get down to something that is the mass of M33, even something like Gaia Sausage Enceladus, or it, a 10-to-1 merger, is not going to bring in very many stars. It's going to be something that is very dark matter dominated. And so there are 2 implications for this, for the stellar halos of M33-like galaxies. The first is that we truly never should have expected to find very many accreted stars in the stellar halo of this galaxy, just because anything that's merging with it is just not going to be bringing in that many stars. And so our finding that the stellar halos are in situ dominated passes at least kind of an initial sanity check. The second implication is kind of a corollary, and it relates to why we see stellar halos in these galaxies at all. And that's that, yes, the mergers that are contributing to the stellar halo in a very minor way are very, very dark matter dominated, but they still bring in a lot of mass. It's just that mass isn't in stars. Something like a Gaia Sausage Enceladus, we still see the impacts of that in the present day on the Milky Way. And if an M33 merges with something like a Gaia Sausage Enceladus in terms of the mass ratio, it's going to still have a very strong impact on it. Likely even more so because the gravitational potential wells of dwarf galaxies are much shallower than those of Milky Way-like galaxies. It is easier to perturb them. It is easier to reorient their disks, as you saw in some of the movies. It's easier to unbind stars or to perturb them into much more chaotic halo orbits. And so what we are actually seeing here is that we have these stellar halos that are made up of in situ material, but they are heavily influenced by mergers. And so that means that we can still use this in situ material to learn about the merger histories of galaxies. However, there is still a little bit of a puzzle here, which is that we should still see some accreted stars. Like the things merging with these galaxies are very, very dark matter dominated, but they definitely still have stars. You definitely saw stars in the video. So where are the accreted stars? Well, thus far, we have really only been looking at the inner regions of the halo because that is the region of M33 that T-Rex surveyed, and that's what I've been comparing to. But if we move a little further out, we can see that most of these halos rapidly transition from being very in situ dominated out to about 6 to 8 scale radii to being entirely accretion dominated beyond that. And that means that we do actually see signatures of accretion in the outer halos of these galaxies. So if we take this galaxy, this is my favorite galaxy in the sample. This is actually an ultra diffuse galaxy. If we take this guy and we look at the outer halo, we see remnants of this satellite, which again, scales not to scale. They're blown up for being able to see them. We see remnants of this satellite. We see remnants of this satellite and this one. And then like 10 things that look like that, and another 10 that look like that. Now, most of the material in the merger is, I mean, in the stellar halo is going to come from these larger components, these more massive ones that have more stars. But the average galaxy in our Marvel's massive dwarf sample has stars in its stellar halo that came from roughly 20 other galaxies. And so just like Milky Way mass galaxies, these dwarf galaxies are very much ensembles. I'm going to just kind of quickly go over this because I'm going to skip some of this. I want to talk about this. Yeah, I'll just quickly talk about this. So what I'm showing here is basically what the makeup of the most average stellar halo in our sample would be. So what I'm showing on the x-axis here is merger mass ratio for different things that would have contributed to the stellar halo. And on the y-axis, I'm showing the average number of things around that merger mass ratio that ended up in the stellar halo of one of our galaxies. So this is our entire sample melted together and then kind of divided up to make the most average stellar halo you can. And so if we think about something like Kraken, for instance, so a 3-to-1 merger mass ratio, we can see that that isn't really common. Not many of our dwarf galaxies merge with something that's there are a few, but it's definitely your average galaxy, for example, anything that substantial to it. Instead, like your average most massive thing for most of these dwarfs is going to be something more like the Homestream's progenitor or Gaia Celtis, where you're having something that's like a 10-to-1 or 15-to-1 merger mass ratio. And the most common contributor is going to be something more like Sequoia with like a 100-to-1 mass ratio.
These are stellar mass ratios.
These are halo mass ratios. Yeah. That being said, the distribution is very broad here, and we get a lot of variation from one galaxy to another. And reflecting that is the kind of debris that we see in the outskirts of these galaxies. So what I've done here is I have basically removed the central galaxy here from each of these images, and instead I'm just showing the tidal debris from one galaxy that fell into our central galaxy and merged with it. And looking at this, you can see that we do have some very, fuzzy cloud phase mix material, and admittedly, that's what a lot of some emitters look like. But I've picked out kind of the debris that I think is the coolest around some of our dwarf galaxies. You can see, for instance, this thing has a bunch of wraps. So this is definitely a stellar stream. We have this remnant where we have stellar streams and shells. This one looks very shell dominated. And so it looks like we have pretty substantial debris that could potentially be observed in the outskirts of these dwarf galaxies. I don't have access to the navigator, so I'm going to, apologies, rapidly skip through some stuff. I'm just going to quickly show that even though observations of outer halos and dwarf galaxies are rare, we do have some. These are kind of heroic efforts by observers to actually capture the stellar halos of dwarf galaxies. And so the 4 images that I'm showing on the left here are dwarf galaxies where we see these very, things that we look at that we're like, that has to be accretion. Like showing here, shells, these two, we have a clearly tidally disrupting satellite. And at least on a superficial level, these look quite a bit like the debris that we see in the simulations. However, to really do a proper comparison between simulations and observations and understand where the simulations are falling short, which they almost certainly are, because this isn't something we've had constraints on in the past, which means probably this is where we've been hiding some of our simulation sins. We really need a much larger sample of dwarfs to compare to. And the good news there is that we are about to enter the era of wide field surveys. So NASA's next flagship mission is the Nancy Grace Roman Space Telescope. And I'm really excited because I got to update this slide a week ago. So this usually says set to launch May 2027 at the latest. And now we have a public launch date that is like 2 months away. So this is really, really exciting. So Roman's going to be up there taking data really soon. And the really special things about Roman, it's an IR telescope that has the resolution of Hubble, but a field of view that's 100 times as big. That's a big deal because even though dwarf galaxies are very small, their stellar halos are really big still, and they're bigger than the field of view of most telescopes. And so we really need this giant field of view. And what's also really good is that Roman is going to be doing a bunch of surveys. And the high latitude wide area survey is going to map large chunks of the sky much down to like greater depths than we've been able to look at before, which means that we don't necessarily have to target individual dwarf galaxies. We should be picking up some of their stellar halos, I hope, just during this survey. I should note too that, so I'm really excited about Roman, partially because I spent most of my first postdoc thinking about Roman. Some of my funding came from the Roman project. And I was at Hopkins and spent a lot of my time at STSCI. So I very much heard all of the hype about Roman, but there are several other instruments that are also doing amazing wide field surveys. So specifically the Vera C. Rubin Observatory and Euclid Observatory. Well, these are amazing. They're already online putting data out. And so I think that even though we have currently a dearth of data on dwarf stellar halos, the landscape is really about to change. And I don't have much time left, so I'm going to skip over all this stuff, but I'll throw my takeaways up here. So the main things are that stellar halos offer us a really unique opportunity to study the assembly histories of galaxies that we really just don't get anywhere else. And so it's, I'm really, really optimistic about our ability to study the stellar halos of dwarf galaxies over the next decade and learn a lot more about the assembly histories of dwarf galaxies that way. Based on the simulations, it seems like the interstellar halos of dwarf galaxies are pretty in situ dominated, and the outer halos are mostly accretion, but you can learn about the history of the galaxy from both of those components, assuming, of course, that the simulations are correct. So with that, I will take any questions.
Clarification, how do you define stellar halo or points?
Yeah, so the method that I have been using is with orbital circularity. So I've been looking at